Okay, so now we can start talking about what we call the derivative. The derivative of a function just means finding the slope of the tangent line at x equals a. So how do you find the slope of the tangent line at x equals a? Well, you take the limit as delta x approaches 0 of f of a plus delta x minus f of a all over delta x. Now, does it make sense? Like, writing all of that is like a real pain. So the shorthand for all of this is we write f derivative, it's that little tick mark, at a. That's what we mean by the derivative of a function at x equals a. Let's do that in red. The derivative of a function at x equals a. The way we write that is this. What does that actually mean? That just means finding the slope of the tangent line at x equals a. That's all of that. So instead of having to write limit delta x goes to 0 of f of a plus delta x minus f of a all over delta x, we just write f prime a, or f derivative a. So what does this mean? Like, this number written in words is what? Or, f prime 3 written in words means what? So what does the prime mean? The little tick mark. Right, and then what does the derivative actually mean? Yeah, so this means the slope of the tangent line at x equals 3 for the function f of x. Likewise, what does this one mean? Like, if we were to write this in words, what is it? Slope of the tangent line at x equals -2, and then the crucial thing is for the function g of x. But yes. Okay, so that's just a shorthand way to basically tell you, yeah, you're going to have to calculate this limit, but we don't want to write that out. So let's calculate a definition. Or calculate one of these. Example, calculate f prime 2 for f of x equals 3x squared minus 4x plus 1. Okay, so what are we calculating? We want the derivative at 2. We want f prime 2. How do you actually do that? Well, you're going to have to do the limit as delta x goes to 0 of f of 2 plus delta x minus f of 2 all over delta x. Okay, so these are like a bit of work, right? So let's calculate these things here off on the side. What we're gonna do, well, what's f of 2 plus delta x? You're like, okay, that's gonna be 3 times 2 plus delta x, quantity squared, minus 4 times 2 plus delta x plus 1. That's going to be 3 times, okay, you have to multiply all that out. 2 squared is 4, so you're going to get 2 times 2, which is going to be 4 delta x plus delta x quantity squared. Okay, then you could distribute that for minus 8 delta x plus 1. We can distribute this 3. We're going to get 12 plus 12 delta x plus 3 delta x quantity squared minus 8 delta x plus 1. Okay, so I'm going to like rearrange the terms a little here. I'm going to put them in terms of descending order with the delta x. So we're going to get 3 delta x squared. We have 12 delta x minus 8 delta x, which is going to be plus 4 delta x. 12 minus 8 is 4, plus 1 is 5. Yay! Okay, we have one part done. Oh, yes. I see what you're saying. Yes, because there's no 2 there. Yeah, this should be... Okay, so let's erase those. Come back and fix them. This should just be 4 delta x, 12 delta x minus 4 delta x is 8 delta x. Thank you for catching that. We also need to calculate f of 2. That's going to be 3 times 2 squared minus 4 times 2 plus 1. 3 times 4 is going to be 12 minus 8 plus 1. 12 minus 8 is 4, plus 1 is 5. Okay, so now what do we need to do? Well, we have to plug all of that in. So we get limit delta x goes to 0. F of 2 plus delta x becomes 3 delta x squared plus 8 delta x plus 5 minus f of 2 is 5. All of this is over delta x. Okay, now notice the 5's cancel. Like what we've been saying this whole time, this delta x on the bottom is an issue because you can't just plug in 0, so we're going to have to find a function which agrees except at a point, all that stuff. So up till now, our f of x is 3 delta x squared plus 8 delta x over delta x. Notice you can factor out a delta x on top. You get delta x times 3 delta x plus 8 all over delta x. Now those quote unquote cancel. You get a new function g of x, which is 3 delta x plus 8. But most importantly, what can you say about these two functions? Well, f of x equals g of x except when delta x equals 0. In other words, they agree except at a point. Now, because they agree except at a point, that means that their limits will be equal to each other. So you have the limit delta x goes to 0 of our original, what I called f. We'll have the same limit as 3 delta x plus 8. And you can just plug in, because this would be just direct substitution, you can plug in delta x equals 0, which will get rid of this term, because you get 3 times 0. You'll be left with 8. So now we know that the derivative of f at 2 equals 8, which means that the slope of the tangent line at x equals 2 is 8. Boom. A lot of work though, lots of calculation. I'll pause for a moment. Okay. So hopefully you're seeing how these derivatives and slopes of tangent lines, whatever you want to call them, derivative is just shorthand for slope of the tangent line. Hopefully you're seeing how this works, right? You have to do this limit calculation. There's two different formulas you can use. There's a lot of canceling. It basically, you're always, this goes back to what I said earlier in the class, you're always going back to calculating a limit. So how are you actually going to solve this? Well, it involves doing the limit of the secant line to get the tangent line. There are some interesting applications to this, which we're going to talk about now. Okay, we're going to talk about a physics application. Okay, so does everyone know what is meant by displacement? I guess I'll explain that. Displacement is almost like distance traveled. But slightly different. So displacement is always measured relative to a starting point. So let's say you start right here and you start moving around. Let's say you end right here. Okay, does it make sense that the distance that you travel is like you would put a measuring tape along the path? That's not quite what displacement is. Displacement just measures from here to here in a straight line. So if you choose some other random point along the path, like right here, whoa, what the hell just happened? If you choose some other little point right here, the distance traveled would be you'd take the measuring tape along your path and measure that. That's not what we want. We just want to measure this. Okay, so if this is time 1 right here, this would be the displacement at time 1. If this is time 2 right here, this would be the displacement at time 2. Alright, so do you see how you're just measuring how far have I traveled away from my starting point? Okay. So displacement is basically like distance traveled. If you look at the rate of change of displacement, what do you call that? The rate of change of distance. What is that called? If you look at how the rate of change of your distance, what do we colloquially call that? Do we know? If you look at how your distance is changing, what do you usually call that? Yes, awesome. Okay, now in physics, we don't talk about distance, we talk about displacement. So if we're talking about the rate of change of displacement, does anyone know what that is called, the physics term? Yeah, exactly. Okay, so let's talk about rate of change. Rate of change is just slope. Okay, so when you talk about rate of change, you have to talk about the rate of change of some function with respect to the independent variable. So if your function is f of x, you would want the change in f over the change in the independent variable x. So if we're talking about the rate of change of some function f of x, we already know the independent variable is x, so you want the change in f over the change in x. So if we're talking about the rate of change of displacement is the function s, and your displacement depends upon time. You want the change in s with respect to the change in time. Time is always the independent variable in physics, basically. So, what is the name for the rate of change of displacement? We just said it. Yeah, so that's what velocity is. Velocity is the change in displacement over your change in time. Which is actually really interesting because this basically comes down to a derivative. The derivative of your displacement is defined to be the limit as delta t goes to 0 of the derivative of displacement at time a is equal to the limit of delta t goes to 0 of s of a plus delta t minus s of a all over delta t. Now the rate of change of displacement just is velocity. So that is how you find your velocity at some particular time. This is like a really common thing in physics. You come up with you have some function like displacement, and then you're interested in the rate of change of that function. Well, the rate of change just is the derivative, because the rate of change is just a slope, and a slope is just the slope of a tangent line. How do you find this tangent line? With the derivative. And then you write out how do I actually find the derivative? I use this limit, and then that gives you some new function to look at. The rate of change of displacement is velocity. Does anyone know what the rate of change of velocity is? So if you want the rate of change of velocity, what do you call that? What's the change in velocity called? Yeah, exactly. So how would you find the rate of change of velocity? By taking the derivative, and that would give you acceleration. So notice that there's a pattern here. You started off with displacement. You took its derivative and you got velocity. And then you took velocity and you took its derivative and you got acceleration, and you can keep doing that basically. Okay, which is why you have to take this class before you take Physics 140, because there's like a lot going on. Okay, now a lot of the times in physics you have to estimate. So often in physics you have to estimate the derivative using data from an experiment. How is this done? Okay, well, the way it's done is that, remember how the slope of a secant line estimates the slope of a tangent line? That's how. So let me give you an example. So let's say that you have some measurements. Some of them are time measurements and the other are velocity measurements. So for instance, at time 0, your object was traveling at a velocity of 0. At time 3.05, your object was traveling at a velocity of, let's say this is miles per hour, 88 miles per hour. At time 5.88, it was traveling at 147.67 miles per hour. At time, and let's just stop right there. Okay, so let's say that you wanted to, suppose you want to estimate the acceleration of the car at time equals, when are we going to do this? How about, and at time 3.05. Like, how fast was it how much was it accelerating? So all you have is, you know how fast it was going velocity-wise, but what was the acceleration? That's what you want to know. So you remember that, hey, acceleration is just the derivative of the velocity. And how do you take the derivative of the velocity? Well, you would do the limit as delta t goes to 0 of the velocity at time a plus delta t minus the velocity at time a all over delta t. Right? This is the slope of a secant line, and here you can choose one point right here and one point right there. So you can estimate what this might be close to. So we're going to estimate it by looking at the velocity at time 5.88. Actually, let me redraw this one up here. Instead of using the delta t definition, let's do the t goes to a definition. So you would do the velocity at time velocity at time t minus velocity at time a over t minus a. Okay, this is going to be our a right here, the 3.05, because that's when we want to find the acceleration. So your second point, your t could be 5.88, so we would do v of 5.88 minus v at 3.05 over 5.88 minus 3.05. So v at 5.88 is 147.67. V at 3.05 was 88. 5.88 minus 3.05 is, I'm calculating it. Thank you. Do you know what the top number is? Okay, cool. And then you could divide that by 2.83 for us. We'll just put 21.1. Okay, so what does this mean? So if your velocity is miles per hour, then your acceleration would be miles per hour squared. So your acceleration is 21.1 miles per hour squared. That is a nice estimation of the acceleration at that moment in time. So a lot of times in physics, you have like data that you have to use, and you estimate what your acceleration is. So instead of like actually finding the slope of the tangent line, you're like, closest thing I have is my secant line because I have these 2 points. we'll just use those, like close enough basically. Hopefully that makes sense what I'm saying. Like you have these numbers, you can plug them into your secant line formula, which is what I did right here, and you use that to estimate what you think the derivative would be. It's a very common technique. And it makes sense because how do we even find the slope of the tangent line? By taking the limit of the secant line, but unfortunately we can't actually take a limit here because we don't have the functions. So instead we just plug in the numbers and we're like, good enough, like that's the best we can do.